Chapter 17 is our final chapter of organic chemistry. In chapters 12 and 13, we covered compounds with only carbons and hydrogens. In chapter 14, we dealt with carbons that have one bond to oxygen, alcohols and ethers. In chapter 15, we covered carbons that have two bonds to oxygen, either as double bonds in ketones and aldehydes, or as in hemiacetals and acetals. In our last chapter, we dealt with carbons that have three bonds to oxygen, carboxylic acids, carboxylates, and esters. In this chapter, we'll deal with nitrogen as it shows up biologically, mainly as amines and amides, which have a double bond to oxygen. The amides have a double bond to oxygen. In each case, our nitrogens will have the same number of bonds to other things, carbon or hydrogen, as long as it's uncharged. Just like with carbon and oxygen, the Lewis dot structure helps us to understand how many bonds that will be, based on the number of non-bonded electrons that are unpaired. With carbon, we had 4 unpaired electrons and always 4 bonds. With oxygen, we have 2 unpaired electrons and always had 2 bonds. With nitrogen, we have 3 unpaired electrons and we'd always have 3 bonds as long as the nitrogen doesn't have a charge. Amines are any molecules where a nitrogen is bound to carbons that don't have carbonyls or double bond to oxygen, regardless of how many carbons are on the nitrogen. We classify the amine as primary, secondary, tertiary, or quaternary based on how many carbons are bound directly to the nitrogen. This is different than what we saw with oxygen. If the oxygen was bound directly to only 1 carbon, we called it an alcohol. However, if the oxygen was bound to 2 carbons, it became a different functional group entirely, an ether. So primary, secondary, and tertiary were used very differently with alcohols, where it allowed us to determine the reactivity of the carbon attached to the oxygen rather than the oxygen itself. With amines, we classify as primary, secondary, tertiary, or quaternary based on the number of carbons connected directly to the nitrogen. Notice that there is a quaternary version of amine, but we changed the name to ammonium. Nitrogen can't have 4 bonds when it's neutral, but it can have 4 bonds when it's positively charged. We then call it an ammonium to indicate the positive charge. We'll talk about that naming convention in a little bit. For now, the big point is that amines are classified based on the number of carbons that are attached to nitrogen. Here we have a bunch of amines displayed. Try to go through left to right, top to bottom, and identify how many carbons are attached to each nitrogen and therefore whether it's primary, secondary, tertiary, or quaternary. We'll start in the top left. In the top left, we have a tertiary nitrogen because the nitrogen is attached to 3 carbons. In the top middle, we have a secondary nitrogen because there are only 2 carbons directly attached to the nitrogen. In the top right, the nitrogen is only directly attached to 1 carbon, and so it is primary. In the second row, we have a tertiary nitrogen, another tertiary nitrogen, and we have a primary nitrogen. This nitrogen has a double bond to oxygen, which is not a carbon, but it only has 1 bond to a carbon. In the bottom row, we have a primary nitrogen. It's actually part of an amide. And then we have a secondary nitrogen. Again, the double bond to oxygen doesn't make any difference. And finally, we have a quaternary ammonium, a quaternary nitrogen. When we name an amine, it will follow the same pattern of IUPAC, that is systematic nomenclature, that we've seen everywhere else. Amines are actually lower in priority than alcohols, but in this class we'll only do examples where the amine is the main chain, if it's present. Amines are easy to recognize in IUPAC nomenclature, since amines always make their way as a full word into the name, replacing the final E of the corresponding alkane, alkene, or alkyne. Even though amines function a lot like alcohols when we name them, I've noticed that students tend to have a harder time thinking of an amine being at the 2 position on a carbon chain than they do for an alcohol, perhaps because the aldehydes, carboxylic acids, and esters that we just talked about are all only on the first carbon. Amines are not like those and can be anywhere on the carbon chain, as long as we number from the end closest to the amine, which is the same thing that we did with alkenes, alkynes, and alcohols. We have some practice on this slide. But before we get too far, I want to remind you that you already know one amine that has a special name, aniline, which is named based on the aromatic. You can see the structure in the top left. The next molecule in the top row has a 3-carbon chain below the nitrogen. So we'd say that the closest carbon to the nitrogen is the 1 carbon, and we'd give that entire chain the root name 1-propanamine. That accounts for the carbons and the fact that the nitrogen is attached to the first one. The nitrogen has 1 methyl side chain coming off, so we'd say it's an N-methyl 1-propanamine, where the N tells us where the methyl is, and the 1 again tells us where the nitrogen is along that longest carbon chain. The next molecule has 2 ethyl chains and a methyl chain. Since the ethyls are identical, we choose one to be the main chain and the other will be a side chain. It doesn't matter which one. So we say we have ethanamine as the main chain, and the side chains are the N-ethyl and the N-methyl chains, each given N to say what they're attached to. The next chain is a propanamine. If you look in the bottom left molecule, see if you can identify which type of propanamine it is. The full name is N,N-dimethyl 2-propanamine. The 2 methyls on the nitrogen are indicated by N,N-dimethyl, and the nitrogen itself is on the 2nd carbon of propanamine, which makes it a 2-propanamine. Now see if you can identify the names for the last 2 amines. The bottom center amine has 3 carbons in its longest chain, starting from the carbon next to the nitrogen, making it the molecule a 2-methyl 1-propanamine. The final molecule is an N,N-dimethyl ethanamine. Amine common names follow the same pattern as other common names. The nitrogen is treated as the main chain and given the name amine, and then all the carbons are given side chain names without locators in alphabetical order. So for the first of these molecules, we have 2 methyls, we say dimethyl, and we have an isopropyl on the bottom. We'd list them in alphabetical order, ignoring the prefixes di or tri, just like we did every other time. The final name then would be isopropyl dimethylamine. Try to name the other 2 amines in this common form. The only side chain on the next amine is an isobutyl group, making this isobutylamine. The third molecule has 2 methyl side chains, a dimethyl, and we have an ethyl side chain, so we'd say it's ethyl dimethylamine. Since amines are still amines, even when you change the number of carbons attached to the nitrogen, most of the isomers of amines are also amines. But we can have different positions, like the first 1-propanamine that we see on the left versus the second molecule, which is 2-propanamine. Those would be positional isomers of each other. We can also have different skeletons. The first and second molecules both have skeletons with 3 consecutive carbons, but we can also place carbons on either side of the nitrogen or even on all sides of the nitrogen for isomers that have different skeletons as well. Primary amines, like alcohols, are able to hydrogen bond between molecules. But the nitrogen holds on to hydrogens a little bit more tightly than oxygen, which means that it shares hydrogens a little bit less freely, and the intermolecular hydrogen bonding isn't nearly as strong. You can see this in the graph that's shown on the left by seeing that primary amines have much lower boiling points than the equivalent of alcohol. That's because they have weaker hydrogen bonding. Primary amines also have dipoles, but again, these dipoles are weaker than alcohols as the nitrogen is less electronegative and therefore its bonds are less polar. And like everything else, primary amines will have London forces that increase with chain length. That's why you see the boiling points go up as we have longer primary amines. Now look at the change from primary to secondary amines, just based on the structure alone at the bottom. The secondary amine has fewer NH bonds than a primary amine, which means that it has less capacity for hydrogen bonding. That would mean that secondary amines would have lower boiling points than the primary amines, because they hydrogen bond less. Once we have a tertiary amine, there aren't actually any NH bonds at all, meaning that tertiary amines, unlike primary amines and secondary amines, can't hydrogen bond. This makes them much lower boiling and much less soluble in water than primary and secondary amines of similar size. Amines, like carboxylic acids, are sensitive to changes in pH. But while carboxylic acids were acidic and would convert to a carboxylate anion, a negatively charged ion, amines are basic and convert to ammonium cations, positively charged ions. Notice that the ending -ium in ammonium matches the -ium ending that many metals have, since metals also form cations. For example, sodium, calcium, or magnesium. So if an amine is in an acid or even in water, most of that amine will convert to that positively charged version we call a substituted ammonium, or just ammonium for short. Substituted ammoniums are named using all the same considerations as amines, whether they come from an acid-base reaction or whether they're positive because they're quaternary, have 4 bonds to carbon. The big difference, and this may come as a surprise, is that ammoniums aren't named with the ending amine. Instead, they have the ending, wait for it, ammonium. Everything else is the same except if the amine had a special name to begin with. Aniline, which is that aromatic amine, becomes anilinium when it's positively charged. So that's just one form that you have to memorize. Anilinium would be the positively charged form of aniline. So if we have a molecule with an aniline but it's charged, we name it as an anilinium, as in the top right. We have 3 methyls off the nitrogen, making this an NNN trimethyl anilinium. For ammoniums without a special name, we just name it based on the longest chain of carbons, just like we did with amines. On the top right, we have an N-methyl, 1-propanamonium. The N-methyl comes from the single carbon on the left of the nitrogen. The 1 comes from the nitrogen's position on that long 3-carbon chain, which gives us propan. And then the ammonium part at the end comes because the nitrogen is positively charged in this molecule. Now try to name the last 2 molecules. Also, there's no reason to pronounce them, but these are probably the most fun to say. One of the 2 carbon chains on the bottom needs to be the main chain, ethanammonium. The other 2 carbon chain and the methyl are listed as side chains, located at N, for N-ethyl, N-methyl ethanammonium. The final molecule is N-dimethyl ethanammonium. The 2 carbon chain is the main chain, and the 2 methyl groups get grouped together as a dimethyl. Amines can show up in much more diverse and complex ways in our bodies. One common form of amines is as a part of rings. We call rings, aromatic or otherwise, that have atoms besides carbon in the ring itself, heterocycles. So any ring that has a carbon swapped out for like a nitrogen or an oxygen would be a heterocycle. There are an enormous number of heterocycles, but I've highlighted 5 here in red boxes that are particularly important biologically. The top heterocycle, porphyrin, is really important because the center of the porphyrin is often used to hold a metal with an important biological function. The most notable porphyrin is a porphyrin that has an iron at the center, which we call a heme. This is the part of the protein hemoglobin that allows you to carry oxygen through your blood. Also highlighted are the heterocycles imidazole and indole in the top row of the table, which are important parts of some amino acid structures. In the bottom row are pyrimidine and purine, which are the basic structure of nitrogen-containing portions of nucleic acids, like DNA and RNA. I want you to memorize the 5 structures shown to the level of recognition. That is, I'd like you to be able to look at a correct structure for one of these heterocycles and match it with the correct name. Because amines can be structurally diverse and are also charged at blood pH, they can be easily recognized based on shape and charge by proteins. This makes them really effective neurotransmitters. The best understood neurotransmitters, like serotonin, the happy molecule, or histamine, the sneezy molecule, are both amines. Other particularly active molecules, like caffeine, the not-so-sleepy molecule, and nicotine, the molecule that will send you to a doc, are also amines.